student area. So I'll tread water for a minute. Apparently there's a few optional topics that teachers can throw in for calculus, and one of them is something called a hyperbolic function. So there's a function, unlike the sine function, you can describe it a little more easily. E to the x minus e to the minus x over 2. And the derivative is really easy to figure out. We know that the derivative is e to the x. But I was wondering what the derivative of the inverse sine of x is. So how do we do that? Well, we do need the derivative here. This is not important stuff. We're just treading water here for a minute. This is actually called the hyperbolic cosine. But the derivative of that, the 1 over the derivative of the original function, is 1 over this. Now we see the difficulty here. How do I express this in terms of this? Not so easy. That's actually a hard problem. I don't remember how you do it. Sometimes when you get old, you forget things, you know. Probably forgotten more things than you guys have learned. Okay, so, well, I'm missing a whole bunch of people. Oh, and the actual topic today is related rates, which is a really good topic. It's an application of calculus. It's actually going to, probably more than anything else we're going to do, it matters, my mask is upside down. It connects to the real world, so doing some physics or maybe some economics. These problems, I mean, the structure of them, this may help you in some real world situation. But as I say, they're a little tricky, and so I'm sorry that I'm missing so many people. But be that as it may, all right, well, we're going to get back to hyperbolics at some point, I think, even though they're optional. Okay, so what's a related rate problem? It sounds, it's like it sounds. You have two rates and they're related in some manner. So I'm going to take a really easy kind of problem here. Easier than anything you'll see in the book. So I have a pipe. And pipes. A bigger pipe might connect to a smaller pipe. Smaller pipe would connect to a bigger pipe. And just to make it easy, this has a radius of 1. This has a radius of 2. So, the area of the pipe is just going to be pi r squared, or the area of this is going to be 4 pi, just pi. And we have a little floater here. It has neutral buoyancy. Any scuba divers here? Neutral buoyancy just means it's just going to go with the water. It's going to go up or down with the water. And it's traveling down at, let's say 1 centimeter per second. So we've got another little floater here on the top of the water. And it's moving down too, right? Well, clearly, the rate that this is going down is going to be related to the rate this is going to go down. And it shouldn't be that hard to figure out. Okay, like, you're only getting 1/4 of the fluid through here that you're getting through here. So, we want to venture a guess how fast this is going to go down. This might explain why when you fill up your bathtub and you open the drain, it doesn't just go whoosh. Right? It's got to go through that pipe. Think about that for a minute. This has got per kind of section here. This has 4 times as much water, right? So if this is going down 1 centimeter per second, this is going to go down faster or slower? Sure, Kevin?
It's going to go slower.
It's going to go slower. Clearly. Your bathtub doesn't go whoosh. Well, how much slower?
1/4. So now it's just
Yeah, it's just going to go down at 1/4 centimeter per second. So these rates are related, right? This is a very simple relationship, right? If we're squeezing water through a pipe, through a small pipe and through a big pipe, and it's going to go faster through the small pipe. Well, so let's just break that down. Rate big pipe is equal to what? 1/4 rate small pipe. And we get that 1/4 by looking at, the areas. We know everything else is the same. Right? Now, I'm not going to answer this question yet. What if, instead of a pipe up here, you have a funnel? That's not as easy a problem, is it now? Because first of all, as the water moves down, the rate's going to change. The same number of water is coming through here, but every time this moves down, and when it's moving down here, it's less water. Here it's more water. So to begin with, if I want to know the rate that this little floater is going down, I have to know where. Like, where is it in the funnel? So this is an example of a related rates problem. We know the rate is related, but we want to find it. All right. So how do we go about this? Let's think about this for a minute. Before we actually get to a problem we're going to solve, I just want to give you the outline for these problems, because there are a lot of different problems. You're going to need some special knowledge outside of calculus that you should have, but they all have a very similar structure. Structure is we're going to use the chain rule. Often x here will be t, as in time, and we'll have one of these. One of these will be given, one of the rates, and we'll have to figure out the other rate. And the special knowledge we're going to have to add is probably geometry, either areas or volumes. There are other possibilities. We'll see other possibilities. So again, we're gonna use the chain rule, and then we're gonna have to think, how do we find this other relationship? Okay, so let's see a real example. This example, very common, involves a balloon. Balloon has a radius. We're hooked up to, I don't know, we divers here, so just an air tank. And we open up the air tank, and air is flowing through this pipe here at 100 centimeters cubed per second. So constant rate here. We're filling up a balloon. The balloon gets bigger and bigger and bigger. I'm going to ask the same question, and it's going to have the same kind of answer. As it gets bigger and bigger, what do we expect about the radius? Is it going to expand quicker and quicker as you get really big, or is it going to slow down?
It'll slow down.
It'll slow down, right. As the balloon's getting bigger, and to increase the radius, you need that much more. So, again, we're going to use the chain rule here. But we want to get the right variables. Oh, what's the question? My question is, how fast is the radius increasing when the radius is 25 centimeters? In other words, words, at that moment in time, when it's about 25 centimeters, how fast is the radius increasing? We know that relate is related to the rate that we're filling up, filling up from our tank, but it's a complicated relationship. It's not simple like my pipe example. So the first thing we want to do is get the variables right. We have a change in volume with time. And we're going to write it this way, using the chain rule. Change in volume with respect to the radius times change in radius with respect to time. Now, it's probably a good idea when you're doing these problems that you're kind of lost, is to just do this mechanically. Just write down an expression that provides you the variables we're dealing with. And then take a look at it. What do we have? What do we need? Well, we have the change in volume with time. Right? That's this volume per second, 100 centimeters per second. So a little check mark here is 100 centimeters cubed per second. Change in radius with respect to time. Well, that's what we want to know. Question mark or X. So what this question boils down to is, what is this? The change in volume with respect to radius. All right, so that's where our real challenge of these problems come. We have to find out what the relationship between the volume and the radius is. Now, does anyone offhand know a relationship between the volume of a spherical balloon and its radius? So this is where we have to go back to maybe freshman year, sophomore year in high school. Learned all those volume formulas. Anyone? Nope. Oh, goodness. Thought I heard something. I guess I'm just hallucinating. Well, I have a little digression here. So let's see, the diameter is equal to something times the radius. Now, I know you know this. Someone, please.
Yeah.
Thank you. Circumference is what? 2 pi. The area of a circle is pi r squared. Okay, now we get a little trickier. The volume of a circle is absolutely is 4/3 pi r cubed. And just to complete the rounds here, what's the surface area of a circle? What's the surface area of a sphere? Anyone know that? Now, those of you who are really good with the power rule, like where it just happens immediately in your head, might notice something curious here. It's 4 pi r squared. curious. I found the derivative of the volume with respect to the radius. I get the surface area. Something to be investigated in the future. Okay, so back here. I want dV/dr. I don't know dV/dr. But I know that volume with respect to r is 4/3 pi r cubed. Oh, but I can differentiate v with respect to r. I guess I already did. dV/r, keep it lowercase r, is 4 pi r squared. All right, so let's write out this equation. All right, it's going to leave off the units. 100 equals 4 pi r squared times, I'm going to say x, because x is what I want to know, right? Or x is equal to 100 4 pi r squared. And I want to know what the rate of change of the radius is when the radius is 25 centimeters. So I can just plug that in. Okay, let's just do a little sanity check here, see if this makes sense. What if you decide is going to happen to the balloon as it gets bigger and bigger? The radius, the rate of change of the radius is going to slow down, right? Does our answer make sense there? Yeah, this is the rate. Put it back. This is r dt. That rate, as r gets bigger and bigger, it gets smaller and smaller. Not that it makes any sense, but if you go in the other direction, as r gets smaller, the rate that the rate r is increasing. In fact, if you get down to 0, it's like increasing infinitely fast until it's not 0, which makes no sense, but you know, that will happen. Okay. This is one related rates problem. You probably see something like this again. You'll see others that are different, but let's just go through the structure again. Kind of look at the problem. We write down the chain rule. We identify the variables. We see what we have and what we're missing. And then, in this case, we have to find some relationship between volume and radius. And then we can find its derivative and we can solve the problem. These are notoriously tricky if you get frightened by something new. But if you're brave about it and you go, wait a minute, I have the knowledge to solve this. They can be very straightforward. They can be very, give you a nice feel when you're done with it. Oh, it just fit together nicely. All right, any questions about this problem here before we're going to try another one. Okay. I'll leave this part out. Maybe small. This kind of problem will show up a lot in physics, but we're avoiding we're avoiding the physics sides of things. Like, in a real physics problem, you might have a balloon, and it's expelling gas, it shrinks, but the rate at which it expels is not constant, right? Like, the bigger the balloon is, the more tension, so it's going to squeeze it out faster. So now we've got a more complicated problem. We're not going to do that problem. That's for your physics class. Oh, I just thought of something. Oh. I can't help myself. Just thinking of something round. Pressure. Wow. This is what we spent like a whole semester on in astrophysics. Kind of all these equations for a star, because you've got, the deeper in you are, the more pressure there is. At some point in the center, and also the temperature, at some point it's so hot and so dense that hydrogen starts doing a fusion reaction, starts turning into helium, giving off energy, and that energy kind of radiates out, and it balances the inward pressure. Does anyone know what happens if, like, there's no energy to keep that balance? This is kind of popular sign. Collapses, right? Anyone know what happens when you have a star collapsing? This is fun. This is fun time. You can't be wrong. Heard of a?
It's really like dense, right?
And then
Yeah.
then different things can happen. You can have what they call a white dwarf, which is held apart by what they call electron degeneracy. It could get even smaller. It's more dense and becomes a neutron star. Everything's a neutron now. All the electrons and protons combine with neutrons, and then you have something called neutron degeneracy. Then, if it gets even denser, everybody knows what it is, right? The black hole, yeah, kind of disappears. Well, it doesn't. The mass doesn't disappear. The mass disappears. The gravity doesn't disappear. All right. It's not a simple related equation problem. Sorry about that. Couldn't help myself. Okay. So in this example, this is different. We don't have any balloons. We just have a ladder, and it's leaning against the wall, and it's also leaning, sitting on the ground here. And at a certain point, it'll hold itself up, but we move it out far enough, and there's not enough friction, and all of a sudden, the top of the ladder starts falling. And due to gravity being a very constant force, in this example, if you ignore, air friction, because there's not much air friction on a ladder. This problem is interesting. In this problem, the bottom is moving out at, I don't know how realistic this is, but it's a math problem, 4 feet per second. And the ladder is 10 feet long. And what we want to know is, how fast is the top dropping? And this is a physics problem. We talked about gravity, but we know Doesn't have to be gravity. This could be out in outer space. This could be just moving at 4 feet per second. Has nothing to do with physics, just a math number. So let's try this strategy again. We're going to write down our chain rule. And let's see what we can do with this. So again, this is a time problem. So I think I'm going to want to keep dy dx in here, so I'm going to make u into t. And actually, I think I'm going to reverse x and y, because this is this is the x direction. That's what yeah. This is dx dt. So let me just change my variables around. I don't like that either. What I want here is dy dt. I want some version of the chain rule where I have y dt and dx dt. Oh, well. Y dx. Okay, there we go. Everyone, I mean, I kind of did that in a haphazard way, but I want to know how fast this is moving. That's my dy dt. I know how fast the bottom is moving. That's my 4 feet per second. I did that kind of ad hoc. I didn't really have to understand what was going on. I just kind of fit the variables to the chain. That leaves me with this.
I have a question.
Sure.
It's kind of hard for me to conceptualize like what dy dt is and what like the other variables are. So like it's hard for me to figure out how to set it up based on like the
Okay.
information you get.
Yeah. Well, let me address your first question first, in case it helps. It might not. dy dt, all right, so this is the y direction. This is the ladder, and we're thinking about, the top of the ladder. And we're thinking about the change in y with respect to time.
Okay.
That's a velocity, right? Here, we've got the x dt, that's the motion outward.
Okay.
It's also a rate, a velocity, change in time. I don't really have a long enough device for this to go slow enough. So I have a wall here, and I just drop this. All right, so this is moving out, and this is moving down. That's kind of what we've got here.
Yeah. Okay, that makes sense.
Okay. That's
And then what about dy dx?
oh, that's right where we are.
Okay.
It's like, dy dx, well, it's the change in y with respect to the change in x. X is up here, if y is up here, x is here. If y is down here, I mean, you can do a little table, just we actually want to know dy dt when this is 6 feet off the ground, right? So let's say it starts up at, can't say 10 feet because it's only 10 feet long, but let's say at 8 feet. And this is y dt x dx dt. So let's say we're up at the top. So y is at 8 feet. It's kind of leaning, it's getting ready to fall. But it's not moving, right? I just haven't dropped it yet. X isn't moving either, so that's 0. Does anyone have any ideas how I'm going to figure out X in this table? Think geometry. It's a triangle. It's 8, 10. How do I find X?
Pythagorean theorem.
Yeah. It's going to be, we're going to know, let's call this X, because that's what it is. 8 squared plus X squared equals 10 squared, or X squared equals 10 squared minus 8 squared, or X equals square root of 10 squared minus 8 squared. Those of you hotshots out there might recognize the ratio of 5 to 4. 5 to 4. 3, 4, 5. Right triangle, right? So what do you know? 100 minus 64 square root of 36. It's 6, not 8. 6. So, as I said, these are in a ratio of 3, 4, 5. Okay. All right. At some point, this is gonna hit bottom, and think of this as like that. You know, as it comes crashing down. How fast is it going? I don't know. But there's a physics question here. Like if I drop something 8 feet, how fast is it going? Use the law of gravity and find out. But I don't know. I'm just going to make something up here, like 7 feet per second. I don't know. Really, it doesn't matter. Don't pay attention to this. X will be 10, and the x dt, well, you know, it's going to stop, but just at that instant, it's still moving at 4 feet per second. So we're interested in how fast it's going. This is, I guess in a way, this is kind of always 4 feet per second. And at 6, well, again, we could use the Pythagorean theorem. Oh, it's going to be 8. Oh, that's nice. So this is what we're looking for, that rate. We've made this very complicated. We've got a nice table here, we've got a picture of a triangle, but really it comes down to what is dy dx. So we need the relationship between y and x, and we saw that, didn't we? Here it is, it's the Pythagorean theorem. So let's work on that. Again, this is always going to be the hard part, which is funny. It's not calculus. Well, up till now, it's not calculus. Okay, so what is the relationship here? Well, the Pythagorean theorem tells me x squared plus y squared equals 100, 10 squared. We want dy dx. How are we going to figure that out? Because we have the tools now. How are we going to do that? Yes?
Do you use implicit differentiation to solve it, or do
You could, yes. You actually have a choice here. I like that. We're going to do that. We're going to follow your idea. We could use implicit differentiation, but we can solve for y, right?
yeah.
We could do that too. Whatever works best. All right, let's do implicit differentiation. It says 2x plus 2y chain rule y prime equals 0. So 2y, y prime equals negative 2x, or y prime equals negative 2x over 2y, which is of course negative x over y. Now we know what to plug in here. So let's write this out. Y dt, again, that's what we're looking for, is equal to y dx is negative x over y times the x dt, which is 4 feet per second. Now, where do we get the x and the y? The problem tells us 6 feet for y. This is 6. And as we figured out, x is going to be 8. And it'd be minus 6. All right, so y dt is negative 8 over 6 times 4 is 32, negative 32 over, that's the right answer, negative 16 over 3. Anyone want to think about, no, it's the wrong answer. Oh. Maybe I read the problem wrong. Oh. This problem is fine, and that's a fine answer. The problem actually wanted it to know the rate when this is 6 feet. This is I think this is the problem in the book. So if I just switch these, 6 and 8, 6 and 8, I'm going to get minus 3. No, it's a different problem. So you can pick any distance here now, and we can plug in and find out how fast it's going to go. Any thoughts on why it's a negative 3? Have any thoughts on that? What that might mean? Yeah, the direction, exactly, going down. All right, so another related rates problem. Here, x and y are related in some manner, completely different from the balloon problem, but the same basic structure. You use the chain rule on these problems. So your chore, your difficulty will be to look at the problem and figure out what that relationship is. You know calculus, so you can find the derivative you need and just plug everything in. almost like there's an easy part and a hard part to these problems. The easy part is the calculus. It's just a simple A equals B times C. The hard part would be the rest of it, the geometry, or whatever else you need. You need some physics or something like that. It's not working the way I thought it would. Yeah, I think this is a good moment to take a break for a few minutes. If you have questions about this and you didn't want to raise your hand up, you can come and ask. let's try a problem. Water trough with a vertical cross section in the shape of an equilateral triangle, one vertex down. It's filled at a rate of 4 cubic feet per minute. Given that the trough is 12 feet long, how fast is the water level rising? Specifically when it reaches a depth of 1.5 feet. So, picture here, like water trough from, like a western where the horses drink. And you've got a faucet coming in at 4 cubic feet per minute. And when it reaches 1.5 feet, how fast is it rising? And this is 12 feet long. So take a few minutes, see what you can do with that. It's usually easier with paper. As you can do it on a tablet. While we're working on that, does anyone know either Kai or Serena? Do you know why she hasn't been in class? I mean,
I'm right here, I'm Kai. I'm Kai, I'm right here.
the other Kai.
Oh,
I'm sorry. You're the K Kai. This is the C Kai. Anyone know why? I mean, are they out sick or no? Oh, it's a bit. How many people are in your freshman class? Anyone know? No idea. Anyone feel like they want a couple more minutes here? Are we good? Okay, let's start real slow. What are the variables here that we're going to deal with in this problem? What are the knowns and unknowns? I give you one variable. Horses, hooves, how many hooves, how many troughs? I mean, that's a good place to start, right? What are the variables here? Somebody give me a variable. I want a variable. Yes.
Dividing x, maybe 40 or 40 unit.
So dy dx is
Dividing t,
dividing t cubic feet per second. Okay, so that's actually a rate.
Yeah.
You gave me two variables. I'll take them. Right? Cubic feet is volume, right? And t is time. Doesn't matter the units right now, but cubic feet and seconds. Okay. That's two variables. You're usually going to find at least three variables. You could find four in a related rate problem if you have one rate related to another rate, in which case you're just going to use the chain rule again. What's the third variable? Thank you, Levy. If you can't find the three variables, you're going to run into a brick wall here. So anyone? And there's my cubic feet. Time is just ethereal. What am I missing? Right there in the problem. This is depth. You can call it what you want. We can call it h for height or y for y coordinate. We're used to using y, so let's try that for depth. And that will, just while we're on it, the units will probably be what? Feet. Thank you. Okay. So Levy was kind enough to give us a rate here, y t. That's going to fit in somewhere with the chain rule. Oh, actually, not sure. Did you mean this, the depth per second? Or you said the volume, right? Yeah. Oh, you meant depth? You get your choice. You could.
Volume.
Volume, okay. All right. dv dt. So, someone suggest a way to finish the chain rule here for me. Yes, Tony? VEY, okay, now stop there, I'm sure you have the rest of it. Someone else has to tell me the rest of it. Yes,
DYDT.
DYDT. Again, we can do that kind of mechanically and look back and think about what that means. VDT, volume with respect to time, that's it's over here. It's being filled at 4 feet per minute. 4 cubic meters per minute. That's what we got here. What else do we know? Or not know? Well, we want to know the rate that it's rising. Which of these rates is that? DYDT, right. That's my unknown. So to find my unknown, I need dV dy. All right. Finally, we get to do some geometry. Now I need to know the volume of a trough. Any kind of general thoughts on this? Yes?
Can we just find the area of the triangle and then multiply it by R?
Okay. I guess the question is which triangle?
Yes.
Kind of this triangle, isn't it?
Yeah.
Yeah, that triangle. Okay, well, let me make it a little easier by turning the triangle over. And I'm just going to call it H for now. That's really Y. But, and it's equilateral. Anyone remember how to figure out the area of this triangle here? Okay. We need to digress a little more. So let's start with something we can kind of get a handle on. Say I have an equilateral triangle and its sides are 1. So it has a base, not base, a height and a base. Base is 1. I don't know what the height is yet, do I? But I do know this height kind of bisects these triangles, so they're congruent. Means these two are congruent, which tells me I know the length of one of these sides of this smaller triangle. Well, 1 divided by 2 is a half. So each of these is a half. And then I have a right triangle here, and I have 2 sides. I have the hypotenuse and a leg. So I can use the Pythagorean theorem. Square root of 3 over 2, that's my height. And if I wanted the area of this triangle, it's 1/2 base times height, so square root of 3 over 2 times a half times a half, or square root of 3 over 8. Well, this is kind of basic math will crop up again in this class somewhere. It's good to note that we have certain ratios here we can count on in an equilateral triangle. If one of the sides is 1, and the height is square root of 3 over 2, they're in a constant ratio. So if I happen to know the height, right, h, I know this is some multiple of h, right? It would be 2h over square root of 3. I guess this is what makes these related things problems difficult, because we haven't taken geometry in a while. But that's kind of the way math is. It just kind of keeps building. There's a few things you can forget and go look up later, but you at least have to have an idea where to look. All right, so this is y, and the side is 2y over the square root of 3. And, you know, it's an upside down triangle, but you think of this as the base, so it's 1/2 base times height, or y squared over square root of 3. That's my area, but didn't we say we want the volume? So it's going to be the cross section, that triangle, area of that triangle, times the length, which is 12. So the volume is equal to 12 square root of 3 y squared. Right, where do we go now? Remembering, we're still looking at this. We know the volume in time. We know we're looking for the change in y with time. And now we have an expression with b and y. Now we get to do some calculus. So what's dv dy? I'm feeling a little cold in here. No one? Thank you. See, you have service. Hang on. Anybody else? Anyone else find the derivative of this? Nope. This is trivial at this point, right? Just the power rule, right? All right, thank you, Jack. Just 2 times this, right? 24 over square root of 3 So we plug this in here, and what do we end up with? We have 4 equals 24 over the square root of 3 y times our unknown. Or our unknown is 4 times the square root of 3 over 24 divided by y, where y is what? The level at 1.5 feet. So we can just plug in 1.5. I feel like I'm not quite getting this across. All right, let's try another one. Let's try a nice easy one. Oh, it's easy. The point is moving on the straight line, x plus 2y equals 2. Given that the x coordinate, that its rate of change is 4 centimeters per second. What's the rate of change in the y coordinate? Try that for a few minutes. Okay, let's try it in the same order again. What are the variables here? Right. Yes, Kevin?
Centimeters, seconds.
Again, that's a rate, that's two variables, right? Centimeters in the x direction, right? In time. So we got the x, and we got the time. And what's the other variable? Thank you, by the way. Yeah, y. So we have, well, I guess I'm gonna write it over here. The x dt, dy dt, and the chain rule tells me that what's the missing piece? This is the place where you can kind of looks like a fraction, so you can use that fact, even though it's a rate. Okay, so what do we have here? We have the x dt, that's a given. We want to find dy dt. Are unknown. So now we have to figure out what dy dx is. I'm going to put this into slope intercept form. So what's my rate? It's my dy dt, I mean dy dx. Yes, Kevin?
Negative 1/2.
-1/2. Okay, so our unknown is -1/2 times, what was our given, 4 centimeters per second? So it's just -2 centimeters per second. Looking at this diagram, we can see what the negative has to do with. This is our line. We're moving up in the x direction. In the y direction, we're going negative. So it's just something to check. Make sure it makes sense. All right, that's as easy as they get. There's some pretty standard problems you run into, and the next one is pretty standard. I get the feeling it's going to be very hard, yet it shouldn't be. Let me start with a geometry question. I have a cone. Got radius r and height h. Its volume is what? The volume of a cone. Okay, let's do some, I will call on you in 1 second. Thank you. Thank you. I'm going to do some statistics here. How many people took geometry more than 3 years ago? ask anymore. All right. I don't know where to go with that. I can't stop calculus class to do, or I guess I could maybe. I could do all of geometry in one class, but I don't think people would absorb it. This is necessary, unfortunately. Yes, you were going to say.
So I'm not sure, 3 would be power cubes.
Well, I'm so dumbstruck looking at that, I can't figure out if that's right or not, but I know how to. Did you say R cubed? No, I know it's wrong. Okay. So, way to kind of remember this is cylinder is the area of each end times the height. So it's the volume of the cylinder is going to be h times pi r squared. You were close though, and you're a lot closer than anybody who didn't answer. So to go from a cylinder to a cone, you add the factor of 1/3. This is also the case if you have a pyramid. You could either have a base, square base, or a triangular base. So whatever the area is, it doesn't matter. It doesn't actually have to be a square. Let's just take a square. So it's got a side, and a height. So if this were just a rectangular volume, it would be s squared times h. But because it's a pyramid, we just add the factor 1/3. All right, glad we get that out of the way. Let's leave this here. So in this problem, you know, you have a water tank. Never seen a water tank. Looks like this. You can imagine having one and putting one together. And the base is 2 feet. And from the base to the bottom is 4 feet. It's inverted and it's dripping at 2 meters cubed per second. That's not dripping, that's pouring out. So the question is, here's the level here. I'll just call that for the moment H. This is going down, and when it gets to 3 meters, how fast is it going? Well, we talked about this. When it's at the top, it's going to go slower. And this is a constant. There's more volume up here. As you get further down, it's going to go faster and faster. So we want to see that in the answer. So what are our variables? Well, let's not forget this is time-based, so time will be 1. I'm calling h here. That's our depth. And what's our third variable?
Is it volume?
Absolutely, it's the volume. So we know we want to know the HDT. That's the rate at which it's coming down. We know that the volume is decreasing at 2 meters cubed per second. So we just have to fill in here the chain rule, dBdH. So again, we know this, we want to find this. That's the crucial piece, dBdH. So we need an expression for the volume when the height is at h. That's not so clear. We knew the radius at h. We could figure it out. Anyone see what the connection here is? Again, it's a geometry thing. I think someone saw this earlier when we talked about this. Take a look at this triangle here, which has sides H and R. And then we're given that the cone is 4 feet tall and has a diameter of 2 feet. You should see something similar about those triangles. They're similar triangles. So we know they have, their sides are in a common ratio. So how shall we write that? H over R equals 4 over 2, or H equals 2R. But now we can express the volume in terms of H. Right? The volume here was 1/3 pi. Oh, now we're using the right variables. R squared H. I can solve for R, right? R is H over 2. I can substitute that in here. And I get 1/3 pi, oh, we're going to have a 4 over there, right? 12 H cubed. Now I can find my derivative, right? I want dV dH. So my derivative here, of course, is 1/4 pi H squared. So let's write this all in. This is 2 meters cubed per second. This is 1/4 pi H when H is 4. And that equals, oh, and that's multiplied by the HDT, which is what we want to solve for. So that's all we need. Solve this simple equation. I'm going to put R back in here, or H back in here. Let's do the sanity check. We're going to divide by this. So as H gets bigger, in other words, as we're up higher, the total value gets smaller as we expect. I guess I should write that out. The HDT equals 2/1/4 pi h squared. So again, as h is large, this value is smaller. And as h gets smaller, this is going to start going down faster. All right. Okay, I think that's enough. If you're having difficulty with the geometry, bring some of the problems that are in the homework to my office hours, and we'll go over them. But we can talk about what we can do to remedy the deficiency if there is one in geometry. I hope it's like riding a bicycle. You get back on it and come back to it. All right, thank you. Have a good weekend.